you've covered these. Under quadratic theory, these were called, well, at least this specific kind was called a quadratic identity, okay? So I'm just going to rehearse the way it goes through because I don't know how many of you actually remember anything from back then, and maybe you sort of rushed through it because you were focusing on the roots and coefficients or something, or who knows. So how does this work, okay? We're going to do this in much the same way we've been doing things already, which is that when you've got two things, you know that they're equal to each other, right? And importantly, you've got, like, say, you know, x squared terms, right? They never mix with x terms. I mean, you can factorize them, but they're still two different things, right? So all of the x squared terms over here must be equivalent to all the x squared terms over here, whatever they are, okay? So we can do some comparisons of coefficients here on both sides, and then we'll move on and we'll do an example with higher degrees, so you can see it's basically the same idea. Okay? So the way this would work is, I'm just trying to think. Yeah, I'm going to take the right-hand side. Okay? And I have to expand it out. There's no kind of shortcut way for that, right? So I've got A outside of that plus expand this, and you got that flying over on the end. Okay? Expand this out properly, so I've got ax squared x a. Okay? Now, because where I'm headed towards is comparison of coefficients, right? I want to put this into a form that makes the comparison easiest, okay? So I've got my x squared, my x, and my constant on the left-hand side, so I'll do the same on the right-hand side, right? Gather all the x squared terms of which there is only one, right? Namely ax squared, so I don't need to touch that. But I do have a pair of x terms, right? I've got this 4ax. You may even want to get out some colors just so you don't confuse things, right? And I've got that bx flying on the end. So to make the coefficients stand out, I'll stick them in brackets. Okay? And then lastly, I've got this 4a, 2b, and c, and all of those together comprise this constant term. Okay? Okay, so again, I put it in brackets, not because I have to, but because it looks elegant, like Brendan does right now. Okay, so now I can say by comparison of coefficients. Because there's just the one x squared term, right? I can straight away say a is going to be equal to 3. No problems. Okay. Likewise, I can say 4a plus b is equal to minus 4. But because I already know what a is, right, I can say that's 12. So this is minus 16 by the looks of it. Yep, that all checks out. Okay. And then lastly, this minus 7 is equal to all those together, right? So let's substitute it in. I've got 4 times 3, which is 12. 2 times minus 16, which is minus 32. This is minus 20, so I'll add 20 to both sides, and that'll give me 13. Okay. Now, in this case, the question was, find A, B, and C. So I actually am done at this point, okay? However, occasionally, they'll just reword the question just a little bit, and they'll say, write 3x squared minus 4x minus 7 in the form this, right? So in that case, all that's left to do is to take my A and my B and my C and rewrite it, like so. 3x squared minus 4x minus 7 is equivalent to, for all values of x, this. 3, 16. Now, what is this called? This first quadratic that we started with, right? It's a quadratic, and this is the way they use the language, in x, right? So x is the thing that's being squared, and x is one there, and so on. So what I've got here on the right-hand side, and down here, right? This is a quadratic in x plus 2. Okay, so x plus 2 is kind of like my variable, right? But sometimes they'll ask you for a quadratic in this or that or the other, and this is what they actually mean. It's all in terms of x plus 2's. Okay. Right, now, just to move on to the next one, I'm not going to finish it off, but just show you how the same principle works, okay? 5a, 5b says that 2x cubed minus 8x squared plus 3x minus 4 is equivalent to this, okay? So it's going to work in exactly the same way. I'm going to have to expand out this right-hand side. And I'll just give you a tip which goes back to sort of year 7 and is a topic which you'll revisit in year 12 called binomial, but just to make things a little quicker for you. When you're expanding out things that are cubed, okay, the way that if you take any kind of polynomial with 2 terms and you cube it, okay, the coefficients of all the terms are going to come from the third row of Pascal's triangle. Do you remember that? 1, 1, 1. And when I say third, I'm counting this as the 0th row because it's kind of a loner. It's not really useful for any math, really. So this is the third row. So that 1, 3, 3, 1. Okay, those are going to be my coefficients. So this is going to be 1 lot of a cubed, 3 lots of a squared b, 3 lots of ab squared, and 1 lot of b cubed. Okay, and if I raise it to the power 4, I just take the coefficients from the next line. Okay, now why is that? Well, if you can be patient enough to wait 12 months, I'll explain. But for now, you can just use this. It'll just save you a little bit of time rather than actually doing this and then multiplying it and expanding the whole thing out. You're gonna land on. Let's do it together. Outside of 1 lot of that. 3 lots of this, 3 lots of this, and 1 lot of that. Okay. The signs alternate, by the way, because of that -1. Yeah, just be careful. Plus, by the way, can you see again? 1, 2, 1, just like Pascal's triangle. Plus this. Plus this, and you're going to do the same thing that we did here, rearrange everything so the coefficients are nice and they line up properly, and then solve it. That's all.